I'm Dr. Sachi Singh from Applied Science and Humanities Department. I'm an assistant professor at Akgec, Ghaziabad. So let's start today's lecture. So today I will discuss the molecular orbital diagram for the heteronuclear diatomic molecules. This is the lecture number series 2nd. So heteronuclear diatomic molecule. Firstly, we define what do you mean by heteronuclear diatomic molecules. So diatomic molecules with two non-identical atoms are called heteronuclear diatomic molecules. The two non-identical, suppose if we talk about homodiatomic, so the both atoms in that diatomic molecules are same type. For example, O2, N2, B2, C2, so both atoms are same. For the heteronuclear diatomic, the both atoms are different. That examples are NO, CO, HF, CN, HCl, etc. Now comes upon that these heterodiatomic molecules have different atomic orbital energies. That means in heteronuclear diatomic molecules, the atoms are different. So their atomic orbitals have different energies. That means the more electronegative atoms have lower energy, while the less electronegative atom has higher energy. That means suppose the two atoms are made up of two different atoms. Suppose it is two different atoms. The atom which is highly electronegative, if it is highly electronegative, that means they having a strong tendency to attract with electron. So they are strongly attached with the electron, that means they are more stable. If it is more stable, that means they are lower in energy. Lower in energy, that means it is close to the bonding molecular orbitals, which I had already discussed in the lecture series number 1. And the less electronegative atoms, that means it is less attracted with the electrons. If it is less attracted with the electron, that means it is less stable. If it is less stable, that is higher in energy. And if it is higher in energy, that means it close to the antibonding molecular orbitals. That's why the heterodiatomic orbitals, the basic difference in that homo and hetero, the configuration is same, but mainly when we draw the diagram, the both atomic orbitals are not on the same, they are in the different depending upon the electronegativity. Now the next one, the unequal contribution to the molecular orbitals. That means because of the energy differences, the molecular orbitals are not shared equally. Okay, the molecular orbital wave function shifted towards the more electronegative atom. More electronegative, that means that electronegative atom are towards the bonding, which I have just already discussed here. Now that they does not have a perfect symmetry, as in when we talk about the homodiatomic molecules, what will happen there? The orbitals are equals, both atoms are same, so they are having equal energy, then they combine symmetrically. But in heteronuclear diatomic, this symmetry is broken due to both atoms are different in nature. Again, now I'll discuss one with the help of diagram. Suppose this is the diagram for the homodiatomic molecules. Okay, so in that case, suppose we take example of A2 or we take any other molecule example. Suppose we take N2O2. So both atoms are same. So their energy order is same. Their energy order is same. Atomic orbitals are in the same position because both atoms are same. But in case of heteronuclear diatomic, both atoms are different. They having a different nuclear energy. Suppose atom A is slightly less electronegative as compared to B. B is suppose more electronegative. If it is more, because they are having different energy, nuclear energy, so if it is more electronegative, so they have a tendency to attract with the electron is more as compared to the less electronegative. It is strongly attached with the electrons, so it is more stable. More stable, so suppose energy order is in this direction, it is more stable, so it is lower in energy. Lower in energy, that means towards the bonding molecular orbital. We had already know that this one is the lower one, that is called as bonding molecular orbital. This one is bonding molecular orbital, or that which is higher energy, that is unstability, that is anti-bonding molecular orbital. Anti-bonding molecular orbital. So always remember, when you draw the diagram, the electronegative atoms are towards the bonding side, or the electropositive or less electronegative atoms are towards anti-bonding side. That's why when we draw the molecular orbital diagram, or when in case of heterodiatomic molecule, that molecules are slightly polar in nature as compared to the homodiatomic molecules. They are purely covalent. They are also covalent, but slightly they are towards the polar side because of the difference in the energy. Okay, so these are the certain basic concept. Now we explain or take some examples of the heteronuclear diatomic molecules. First example is a NO molecule. The NO molecules, that it is a heterodiatomic because made up of two different atoms. One is nitrogen, other one is oxygen. So in nitrogen, as we all know that its atomic configuration, atomic number is 7. So its atomic configuration is 1s2, 2s2 and 2p3. And for the oxygen, it is 1s2, 2s2 and 2p4. So as when we combine 7 plus 8, the total number of electron is, here the total number of electron is 15 electron. So we have already discussed that when the number of electron is more than 14, then it follows the case second of molecular orbital configuration. There are two cases which is discussed in the previous video. One is case 1, when the number of electron is less than 14, and the case less than or equal to 14, and the case 2, when the number of electron is greater than 14. So here for the NO molecule, the total number of electron is 15. So it follow the case second. So in that case, electronic configuration for the NO molecule. So NO molecules, when electronic configuration, we all know that the nitrogen 1s2, 2s2, 2p3, oxygen 1s2, 2s2, 2p4. When we draw the diagram or the configuration, bond order or magnetic character. So in case of heterodiatomic, the only difference when you draw the diagram, because when we draw the atomic orbital, their energy is different because made up of two different atoms. But there are no difference during the formation of, you are writing the electronic configuration. The rule and regulation are same as in case of homodiatomic molecules. So in case of NO, suppose nitrogen 1s2, oxygen 1s2. So in 1s orbital, the total number of electron is 4. We know that 1s combined, there is formation of sigma 1s and sigma star 1s. 2s combined, sigma 2s and sigma star 2s. 2p combined, now it is case second. So in case second, firstly written as sigma 2px and then pi 2py and pi 2pz. And then pi star 2py and pi star 2pz depending upon the molecular orbital diagram, because electrons are completed here in this pi star 2py. So that's why written here only pi star 2py orbitals. So electrons are filled because 4 electrons, so 2 and 2, 4, 1s, then 2s, 2p, total p orbitals 4 plus 3, 7 electrons. So we count here in p orbital 2, 4, 5, 6 and 7 electrons. Now comes upon the bond order. How you find the bond order? The number of electrons in bonding minus number of electrons in anti-bonding by 2. So the bonding without star, that is bonding, and that without star, that is bonding. So here the anti-bonding is the star. So this one is star and this one is star and this one is star. So the total number of electrons in anti-bonding is 5, 2 plus 2 plus 1, and remaining are the bonding molecular orbitals, electron. 10 minus 5, so bond order is 2.5. And the magnetic character, how we find the magnetic character? That depend upon the outer orbital's electron. If the outer orbital electron is paired or unpaired. Suppose here the outer orbital electron is 1, so that is unpaired. That's why its magnetic character is paramagnetic in nature. So this is the configuration magnetic character. Now comes upon the diagrams for the NO molecule. So let's see the diagram. So the molecular orbital diagram. So here firstly draw the written as atomic orbitals, molecular orbitals, and then draw the energy order. Suppose this side is for nitrogen, this side for the oxygen. Generally see that in case of homodiatomic, that both energy order is same. So here this energy order is slightly, this is for the oxygen atom, this is slightly lower as compared to the nitrogen, okay, because of the difference in electronegativity. So in that case, so 1s combined, so there is formation of sigma 1s and sigma star 1s. Sigma 1s and sigma star 1s. 2s, this is for the nitrogen, this is for the oxygen. 2s combined, again there is a formation of bonding, and the upper one is anti-bonding. And 2p, as the number of electron is 15, it follows case second. So that's why firstly written sigma 2px, then pi 2py, pi 2pz, then pi star 2py, pi star 2pz, and sigma star 2px. So in that case, so the important thing, this is the case second. So case second, you can consider that case firstly written sigma 2px and then pi 2py and pi 2pz. That is the important for the case second. Now filling the electrons, this is the only block. Here the electrons are not filled. Now fill the electrons. So nitrogen 1s2, 2s2 and 2p3. So here the 2 electron 1s2, 2s2 and 2p3. Okay. So this one, now this electron is shifted toward, now this is completed the atomic orbital for the nitrogen. Now atomic orbital for the oxygen, 1s2, 2s is vacant. Now the 2 electrons filled here, 2s, and now the 2p4. Now the molecular orbitals, now this middle one is the molecular orbitals. So here electrons are filled, 1s combined. So we know that maximum electron in any orbital is 2 and they must have opposite spin. So here the 2 electron bonding and the 2 electrons in anti-bonding. That's why the configuration written as sigma 1s2 and sigma star 1s2. Wait, just and now the 2s combined, sigma 2s and sigma star 2s. The 2p orbitals, the total electron is 3 plus 4 electron, so total 7 electrons. So 2 are filled in bonding. Again, how much electrons are remaining? We have remaining 5 electrons, and 1, 2, 3, 4, and this one is 5th electron. So this is the molecular orbital diagram for the NO molecule. Now the configuration, again can explain that same configuration. The sigma 1 is the 2 electron, 2, this one is bonding, this one is anti-bonding, and then again sigma 2px, pi 2py, pi 2pz, and then pi star 2py is the single electron. Okay, so this is the molecular orbital diagram. Now the bond order, bonding minus anti-bonding by 2. As we already know that bonding electron represented by the star, anti-bonding is without star. The lower energy is the bonding, higher energy is the anti-bonding. Again, you must remind that during the diagram of the molecular orbital for heterodiatomic, the electronegative is slightly lower side as compared to the electropositive. Okay, they are not on the same energy order. They are slightly lower in energy order. Okay, that represent. You may also draw that diagram slightly lower side, slightly in that side, slightly more lower side. So that is more better. Okay, and now the magnetic character, as the outer orbital is paired or non-paired. So it's, there is a single electron, so it is unpaired. That's why its character is paramagnetic in character. So this is the molecular orbital diagram for the NO molecule. This is the heterodiatomic molecule. Now again we take one more examples. Now comes upon the molecular orbital diagram for the CN molecule. The CN molecule, that is carbon, nitrogen, the same way. There is a no change in the configuration. The cases are same. Firstly, we calculate the number of electrons, then we'll decide the cases. We apply the case 1 or case 2. So let's start the CN molecule. So carbon atomic number is 6 and nitrogen is 7. So the total number of electrons in CN molecule is 6 plus 7, that is 13 electrons. So if it is 13 electrons, so which case it is followed? That is, the electron is less than 14, so it follows case 1, where the number of electron is less than equal to 14. So according to case 1, now the configuration is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2py, pi 2py2 and pi 2pz2, because it follow the which case? The case 1. That's why written firstly pi orbital and then sigma orbitals. So this is the electronic configuration for the CN molecule. Now we calculate the bond order, the number of electrons bonding minus antibonding. When we talk about the bonding, how many electrons in bonding? Let's calculate. 2, 4, 5, 6, 7, 8, 9. And that this one is antibonding and this one is antibonding. So 4 electrons in antibonding and remaining 9 electrons in the bonding molecular orbital. So the bond order is 2.5 and the magnetic character, yes, the outer orbital having the unpaired electron, that's why it is paramagnetic in nature. Okay, this is the molecular orbital configuration, bond order and magnetic character. Now comes upon the diagram for the CN molecule. So the CN molecule, again let's start with the diagrams. So here atomic orbitals, energy orders, but the number of electron is less than 14, so that case 1. So 1s again that they having a different electronegativity. So when we compare with the carbon and nitrogen, which one is more electronegative? Nitrogen. Now this one sigma 1 is sigma star, 2s2 is combined, one is formed bonding, other one is formed antibonding. Now comes upon the p orbital. So in p orbital, the carbon 2p and 2p combined. So the case, you can remember the case follow the rule 1, in which firstly pi 2py, pi 2pz and then sigma 2px. So in that case, the number of electrons firstly filled here in the pi orbitals and then sigma orbitals. That is the case 1. So in that case, firstly carbon configuration is, what is configuration? That is written here, 1s2, 2s2 and 2p2. So here that is carbon 1s2, 2s2 and 2p2. And for the nitrogen, 1s2, 2s2 and 2p3. Now the combination, as all we know that always when combined, the electrons move towards the lower or bonding molecular orbital. So bonding molecular orbital, that is sigma 1s, so electron firstly filled in the sigma orbitals and then antibonding sigma star orbitals. So the total 4 electrons, 2 are filled in bonding and 2 are filled in antibonding. Now in the 2s, you can see that both orbitals are different, so their energy order is slightly different. They are not in that. This is the energy level and this is this energy level. Sorry. So their energy level in this. So here the electrons are combined. One is sigma 2s and sigma star 2s, 2 bonding, 2 antibonding. Now comes upon the p orbitals, the total number of electrons, 5 electrons in p orbitals. So 1, 2, because they having a similar, that equal energy. So firstly they filled and then they start to paired up and then 1 electrons in the sigma 2p. So this is the electronic configuration for the CN molecule. So this that CN molecule, so it can written as 1 as sigma 1s2, sigma star, sigma 2s2, sigma star 2s2, pi 2p by 2 and pi 2p z2 and sigma 2px. So this is the molecular orbital configuration and this is the diagram for the molecular orbitals. Now comes upon the bond order. Bond order, just we have to find out also the bond order, bonding minus antibonding. So here the 9 minus 4, that is 2.5. As the outer orbitals, the outer orbital is having unpaired electron, that's why its character is paramagnetic in nature. Okay. Suppose this is for the CN molecule. If the question asks in the examination, draw the molecular orbital diagram for the CN minus. That is CN minus. This is for the CN. If question asks for CN minus, so what changes? Firstly, we find out the total number of electron in the CN minus. So here in that case, the total number of electron in that CN is total number of electrons 6 plus 7, that is 13 electrons. And in CN minus, 1 electron minus, that means 1 electron is added here. 1 electron is added here, then the total number of electron is 14. Okay, that means the same configuration, because when we talk about the ions, we are considered the configuration for the parent molecule, not for the ions, because ions are formed from the parent molecule. So whatever, if suppose CN double minus, the number of electron is 15. So don't change the configuration. The configuration is same for the CN, because CN minus, yes, CN double minus, they are formed from the parent molecule and its parent molecule is CN, whose number of electron in there is 13 electrons. So in case of suppose CN minus, so what changes here? 1 electron is added, so 1 electron is added in that side. Can change the color. So for CN minus, we talk about the 1 electron added here. Okay, if the 1 electron is added here, now that bond order is changed. The bond order is the bonding, the electron is added where? In bonding or anti-bonding? It is added in the bonding. So there it is. For the CN minus, it is written as bond order is 10 minus 4 by 2. Okay. So 10 minus 4 by 2, there it's a number of electron, that bond order is written as, that is 3. Okay. And the magnetic character is, now it is paired. So for CN minus, the magnetic character is diamagnetic. That is diamagnetic. Okay. So whatever the question asks for the CN or CN minus, so in this way you have to draw the molecular orbital diagram for the CN minus also. Or you can add the electron in the electronegative side because they are lower in energy. So if in case of CN minus, the extra electron is added towards the nitrogen side. So this is the molecular orbital diagram for the CN, or also I'll explain some points for the CN minus. So thank you, keep learning, all the best.